Dear students, welcome to the next lecture of organic chemistry. In this lecture, we shall discuss about carbohydrates. Carbohydrates are a class of naturally occurring compounds that are composed mainly of carbon, hydrogen and oxygen. Their general formula is CxH2O times. And carbohydrates were believed to be the hydrates of carbon. Chemically, they are defined as optically active polyhydroxyaldehydes or ketones, or the compounds which produce units of such type on hydrolysis. Examples of carbohydrates include ribose, glucose, fructose, sucrose, starch, cellulose, etc. Carbohydrates are classified into sugars and non-sugars. Sugars are crystalline, sweet, and water soluble. Examples include glucose, fructose, sucrose, etc. While non-sugars are amorphous, tasteless, water insoluble. Starch and cellulose are examples of non-sugars. Based on their behavior towards hydrolysis, carbohydrates are classified as monosaccharides, oligosaccharides, and polysaccharides. Monosaccharides cannot be hydrolyzed into simpler compounds. They have the general formula CH2O n times. Depending on the number of carbon atoms, monosaccharides are divided into triose, tetrose, pentose, hexose, etc. Where triose contains 3 carbon atoms, tetrose contains 4 carbon atoms, 5 and 6 carbon atoms in the case of pentose and hexose respectively. Depending on the functional group present, monosaccharides are classified into aldose and ketose, where aldose contains aldehyde functional group and ketose contains keto functional group. Glucose is an example for aldose and fructose is an example for ketose. Ribose is a pentose as well as an aldose. Oligosaccharides upon hydrolysis yield 2 to 9 monosaccharides per molecule. They are classified into disaccharides, trisaccharides, tetrasaccharides, etc. depending upon the monosaccharide units which are produced upon hydrolysis. Examples include sucrose and maltose. Sucrose and maltose are examples of disaccharides. Sucrose on hydrolysis gives 2 monosaccharide units, 1 molecule of glucose and 1 molecule of fructose. Maltose on hydrolysis gives 2 molecules of glucose. Polysaccharides upon hydrolysis yield a large number of monosaccharides per molecule. These polymeric compounds are joined together by glycosidic linkages. Examples include starch, cellulose, glycogen, etc. The three-dimensional structures which contain At least one asymmetric carbon atom can be represented on a two-dimensional surface with the help of Fischer projection. The four different groups attached to a chiral center are placed at the four ends of the cross, and the chiral carbon is assumed to be located at that point where the two lines cross. The Fischer projection of glyceraldehyde is shown here. It has one chiral carbon which is represented at the junction of two lines, and the four different groups are shown here. The D and L isomers of glyceraldehyde are represented here. The isomer in which the OH group is towards the right side is called D isomer, and in which the OH group is towards the left side is called the L isomer. In Fischer projection, the carbonyl group is always represented at the top. So here the aldehyde group CHO is represented at the top. The D and L isomers are enantiomers and they are mirror images of each other. In glucose, there are four chiral centers and hence the Fischer projection is like this. The four chiral centers are 1, 2, 3, 4. The CHO group is represented at the top and the CH2OH group is represented at the bottom. The OH and H groups are represented towards the left and the right side of the molecule. In glucose, if we consider from bottom, the configuration is D, D, L, D. That is, the first chiral center from the bottom has OH group towards the right. The second one also OH group towards the right. In the third one, the OH group is towards the left. And the last chiral center from the bottom has the OH group towards the right. And hence the configuration from the bottom is D, D, L, D. The L-glucose is the mirror image of this molecule. Glucose belongs to the class aldohexose. Aldohexoses have four chiral centers and hence the number of stereoisomers is 2 raised to 4, which is 16. That is, aldohexose has 8 pairs of enantiomers. And glucose is one among them. The Fischer projection of fructose is shown here. Fructose is a ketohexose. The carbonyl group is represented at the top as it is a keto group. It is on carbon number 2. And the other 3 carbons of D-fructose has the same configuration as that of D-glucose. That is, if we consider from the bottom, the configuration of D-fructose is DDL. And then the keto group and then CH2OH. Diastereomers that differ from each other in the configuration at only one chiral center are called epimers. An epimer of D-glucose is D-mannose. There are 4 chiral centers in D-glucose, and for an epimer, the configuration at one chiral center will be different and all other chiral centers will have the same configuration. So if we consider glucose and mannose, we can see that the configuration is different at, at the second carbon from the top. For D-glucose, it has a D configuration, that is OH is towards the right and H towards the left. In the case of D-mannose, the carbon next to the CHO group has H towards the right and OH towards the left. The configuration of D-glucose from bottom is DDLD, whereas that of D-mannose is DDLL. And hence, D-glucose and D-mannose are epimers of each other. Another example for epimer pair is D-glucose and D-galactose. Here the configuration is different on the second carbon from the bottom, second chiral center from the bottom. For D-glucose, the configuration from the bottom is DDLD, whereas for D-galactose, the configuration is DLLD. The second carbon, second chiral center from the bottom of D-glucose has OH towards the right and H towards the left. And for galactose, it has H towards the right and OH towards the left. Thus, D-glucose and D-galactose are also epimer pair.